The double-slit experiment, deconstructed. This presentation offers a rigorous mapping of measurement-induced decoherence, moving from philosophical mystery to precise, empirical calculation. As Richard Feynman put it, this experiment contains the only mystery of quantum mechanics. Our goal is to deconstruct that mystery, layer by layer. The architecture of this mystery was built over 2 centuries. In 1801, Thomas Young used light to establish the classical wave paradigm. Then, in the 20th century, Louis de Broglie's matter-wave hypothesis transformed the experiment. Applying it to electrons provided the first direct evidence of wave-particle duality in massive particles. Today, we tackle the mystery with precision and calculation. Nanofabricated apertures, controlled Witch-path information, and tunable wave packet geometry allow us to actively observe the boundary where quantum superposition transitions into classical probability. To truly understand the experiment, we must first dismantle 3 popular myths. Myth 1. Measurement creates 2 neat physical lines on the detector, like bullets hitting a wall. Myth 2. Interference is a physical force field the electron travels through. Myth 3. A conscious observer mystically alters reality. We will replace each of these with a functional, quantitative reality. The 2 lines are a physical impossibility, forbidden by the Heisenberg uncertainty principle. Interference isn't a physical pattern. It's a non-physical probability distribution defined by the Born rule. And measurement isn't magic. It's the act of destroying structural information, transitioning a system from low-entropy fringes to high-entropy noise. Let's deconstruct the 2 lines fallacy. When you squeeze an electron through a slit, the Heisenberg uncertainty principle forces a massive, calculable expansion in its transverse momentum. As we will calculate, a 50 picometer wavelength electron traveling just over 30 centimeters will spread to roughly 50 micrometers. Without the structure provided by interference, you don't get discrete lines. You get 2 massive, overlapping, featureless washes of gray. The neat bullet narrative is a physical impossibility. Next, the myth of the physical pattern. Interference is not a glowing force field in the air. It is an emergent statistical property. A single electron always lands as a single, localized point. The interference pattern you see in textbooks only emerges from the statistics of thousands of individual wave function collapses. The pattern exists only in the data. Finally, we reclaim information from magic. The act of measurement doesn't change the fundamental laws of physics. It simply destroys the phase coherence between different paths. The magic of the experiment is simply a measurable transition of structural information. We shift from the low-entropy, highly structured data of interference fringes to the high-entropy, featureless noise of a measured system. The 2012 experiment and article by Bach, Pope, Liu, and Batalan confirmed the wave-particle duality of electrons using a modern double-slit apparatus. The setup begins with an electron gun that emits a beam directed toward a wall containing 2 distinct slits. A mask controls which slits are active, while a backstop and detector work together to measure the distribution of electrons after they pass through the slits. This configuration allows for 3 experimental conditions. In Figure B, when only 1 slit is open, the measurement yields either P1 equals phi_1 square or P2 equals phi_2 square, representing the probability distributions associated with each individual path. These results align with the particle-like behavior of electrons. In Figure C, with both slits open, the experiment reveals an interference pattern described by Beta Kamoan. P12 equals phi_1 plus phi_2 square, clearly demonstrating wave-like behavior. For the modified experiment, the apparatus is designed for precision. An electron gun fires 600 electron-volt electrons, giving them a de Broglie wavelength of approximately 50 picometers. Electrostatic lenses focus this beam into a Gaussian wave packet with a transverse standard deviation of 140 nanometers, centered on the 2 slits. The slits themselves are precision machine structures, each 50 nanometers wide, with a center-to-center separation of exactly 280 nanometers. A movable mask and pre-slit detectors allow us to control and measure Witch-path information. After passing through the slit plane, the wave function propagates 30.5 centimeters through a high vacuum to the detector screen. These are the matrix variables, wavelength, beam profile, slit geometry, and flight distance that we control and calculate with to probe the transition from quantum superposition to classical probability. Let's establish the technical foundations by running the numbers. It all begins with the 600 electron-volt accelerating potential. From this energy, we derive 2 fundamental properties. First, The electron's wavelength, using de Broglie's relation, is approximately 50 picometers, the source of its wave-like behavior. Second, the electron's velocity calculates to 1.45 times 10 to the power of 7 meters per second. Given a total flight path of 0.47 meters from gun to detector, the transit time for each electron is 32.4 nanoseconds. This transit time is critical for establishing single electron conditions. To ensure only one electron is in the apparatus at a time, the maximum theoretical firing frequency is about 30.9 MHz. We operate at roughly half that, 15.5 MHz, creating a temporal buffer that guarantees wave packets never overlap in the chamber. Now let's look at transmission probabilities. The electron beam is shaped into a Gaussian distribution centered on the slits, with a standard deviation of 140 nanometers. The probability density at the exact center is 2.85 times 10⁻³ per nanometer. At a distance of 1 standard deviation away, it drops to 1.73 times 10⁻³ per nanometer. Multiplying these densities by the 50 nanometer slit width gives us the single-slit transmission probability. At the center, an electron has a 14.25% chance of passing through a slit. At 1 standard deviation off-center, that drops to 8.63%. With 2 identical slits, the total transmission probability at the beam center is 28.5%, and at 1 standard deviation, it's 17.26%. Finally, we can calculate our expected detection flux. Multiplying our 15.5 MHz operating frequency by the 17.26% total transmission probability yields approximately 2.67 million electrons per second arriving at the detector, about 1.34 million per second through each individual slit. These aren't abstract numbers, they're testable predictions that allow us to verify our understanding of the wave function as it arrives at the slit partition. Constraining the electron to a 50 nanometer slit creates an initial spatial squeeze. This induces a massive transverse velocity uncertainty, forcing the wave packet to expand over its 0.305 meter flight path. With a wavelength of 50 picometers and a velocity of 1.45 times 10 to the power of 7 meters per second, the initial spatial spread of 25 nanometers leads to a velocity uncertainty of over 2,300 meters per second. The result: by the time the electron reaches the screen, its spread has grown to about 50 micrometers, 1,000 times its initial width. The Heisenberg uncertainty principle is not a philosophical footnote. It is a calculable, dominant effect. Scenario 1. A single slit, with no measurement. The electron approaches the slit as a coherent wave packet with a Gaussian transverse profile. Upon reaching the aperture, the slit acts as a spatial filter. It truncates the wave function, producing a rectangular profile at the slit plane. This is not a particle being shot through a hole. It's a wave packet being physically cropped by the aperture. The wave function doesn't wait at the slit and then begin propagating. It is already traveling toward the screen at 1.45 times 10 to the power of 7 meters per second. As it propagates forward, it simultaneously spreads out transversely due to the momentum uncertainty induced by the confinement. At the moment of truncation, the electron is confined to the 50 nanometer slit width. According to the Heisenberg uncertainty principle, this confinement creates an uncertainty in transverse momentum. Over the 30.5 centimeter distance to the screen, a journey of about 21 nanoseconds, that momentum uncertainty manifests as continuous spatial spreading. By the time the wave function arrives at the detector plane, it has expanded from its initial 50 nanometer width to approximately 50 micrometers. In the far-field Fraunhofer limit, the wave function becomes the Fourier transform of the aperture, a sinc function. The probability distribution, therefore, is the square of that, a sinc square pattern, classic single-slit diffraction. The spacing between adjacent minima, from the center of the central peak to the first dark fringe, is given by lambda L/A. Plugging in our numbers, 50 picometers times 0.305 meter divided by 50 nanometers, 305 micrometers. This 305 micrometer spacing is our technical verification that the expansion calculations match the observed pattern. The electron doesn't spread out after the slit. It propagates and spreads simultaneously, arriving at the screen as a fully formed diffraction pattern. Scenario 2. A single slit, but this time we measure which path the electron takes by triggering a detector at the slit. This localization collapses the wave function, destroying its transverse coherence. The Heisenberg uncertainty principle now introduces a massive momentum uncertainty. The result is a complete loss of structure. The distinct diffraction pattern is replaced by a broad, featureless, diffuse spread. A direct demonstration that gaining position information at the slit comes at the cost of destroying the coherent propagation that would otherwise produce a well-defined pattern. Scenario 3. Both slits are open, and we perform no measurement. This is the configuration that produces quantum interference in its purest form. The electron exists in a coherent superposition of paths. Its total wave function, psi total, is the sum of psi1 plus psi2, meaning the electron passes through both slits simultaneously. This is not a philosophical statement. It is a mathematical requirement for the interference pattern that follows. Now let's track what happens to each wave packet after it passes through its slit. As we calculated in scenario 1, constraining each electron to a 50 nanometer slit width induces a transverse momentum uncertainty. Over the 30.5 centimeter flight to the screen, a journey of about 21 nanoseconds, each individual wave packet expands from its initial 50 nanometer width to approximately 50 micrometers. Here's the critical insight. The center-to-center separation between the two slits is only 280 nanometers. But by the time the wave packets reach the screen, each has ballooned to 50 micrometers. This means these two probability clouds overlap almost completely. Their centers are separated by just 280 nanometers, but each cloud is nearly 180 times wider than that separation. This complete overlap at the detector plane is the physical condition necessary for interference. The resulting detection pattern is described by a product of two functions. The first is the single-slit diffraction envelope, a sinc-squared function we saw in scenario 1, which creates the broad 305 micrometer spacing between minima. The second is a cosine-squared interference term, which modulates that envelope with much finer fringes. The spacing of these fine interference fringes is given by wavelength times distance, divided by slit separation. Plugging in our numbers, 50 picometers times 0.305 meters divided by 280 nanometers gives us approximately 54.5 micrometers. So within the broad 305 micrometer diffraction envelope, you'll see approximately 5 to 6 interference fringes, each spaced 54.5 micrometers apart. This pattern only emerges because the paths are indistinguishable. The wave function encodes the complete probability distribution, and each electron detection is a single sample from that distribution. Only after thousands of electrons accumulate does the iconic interference pattern reveal itself, a direct visualization of the coherent superposition encoded in the wave function. Scenario 4. Both slits are open, but we now acquire which path information. The act of measurement collapses the superposition. The electron is now in a definite state, having passed through one slit or the other. The phase relationship between the two paths is erased. The waves still expand to 50 micrometers and overlap, but because they are no longer coherent, they do not interfere. The pattern on the screen becomes the simple, incoherent sum of two independent probability distributions. It is a smooth, broad envelope, completely lacking the fine interference fringes. Let's diagnose the mechanisms. With a single slit and no measurement, we have spatial filtering, governed by a Fourier transform. Adding a measurement invokes the Heisenberg uncertainty principle, forcing a chaotic spread. With a double slit and no measurement, we have coherent superposition, governed by constructive and destructive interference. But when we add a measurement to the double slit, we induce phase erasure. The system transitions from a coherent superposition to an incoherent addition of independent probabilities. This diagnostic matrix summarizes the core insight. The key variable is not consciousness, but information. When the paths are indistinguishable, you get interference. When a measurement makes them distinguishable, you get decoherence. The transition is a direct consequence of the physical interaction that extracts information from the system. Which brings us to the core insight, the price of information. Quantum interference is fundamentally contingent on the indistinguishability of paths. Indistinguishability equals coherent superposition. Distinguishability, gained through measurement, equals decoherence and independent probabilities. The introduction of a measurement erases the phase relationship, transitioning reality from a coherent superposition to a classical-like mixture. The mystery is not magic. It is the precise, predictable, and fragile consequence of information and coherence in a quantized system.